Hello to all of you. This is Dr. Dhaval Maheta, and today we are going to discuss about assumptions of classical linear regression model. Basically, what do I mean by regression is it is a study of dependence of one variable on the another variable, or rather, how one independent variable is affecting the dependent variable. It is a cause and effect relationship where y is called the dependent variable, x is called the independent. Now, this notations in some book is used as regression and regressor or predictant and predictor. So different books have got different terminology. This is dependent variable and its terminology, explanatory variable and its terminology. We are using this equation, which is a population linear regression concept. So y is equal to beta 0 plus beta 1 x plus error term. Why this error term is there, we'll explain later on. It is also known as a random error component. Now, for every change in x or for every value of x, there will be a value of y depending upon beta 1 and beta 0. Beta 0 is a constant and beta 1 is a slope. There are two types of relationship. One is a statistical versus deterministic relationship. So, statistical relationships, if we are having a variables which are random or stochastic variable, that is they are having a probability distribution, then it is a statistical relation. If we talk about deterministic relationship, so it deals with variables that are not random or stochastic. Example, law of gravity. In a simple term, if I say that your equation is having an error term, is a stochastic relationship. Then there is a concept of conditional and unconditional mean. This I will explain in a word file. Now in normal regression, if I talk about cross-section regression, what will happen is that x, y, for every value of x, we may be having some value of y. And we will pass a line in such a way that it covers maximum part. This is cross section. But when I talk about regression in time series, let's see what happens. For every value of x, it may be possible that we may be having many values of y. For example, x is the education, 8 standard, 9 standard, 10 standard, 12 standard, and here is the income. So I have taken a pool of people who have just studied till 8 standards. So there may be the deviations in income like this. Similarly, 9 standard. So it may be possible that this deviation goes on increasing or decreasing. So what you can see is that the mean is changing continuously. See, the mean is changing continuously. Moreover, the deviation in the data, the dispersion in the data is changing continuously. This is the deviation for 10 standard, deviation for 9 standard, deviation for 8 standard. Let us try to understand this by this slide. What is the concept of conditional and unconditional? For every value of x, we will be having a sum value of y. That is a average. So if I say that if the income is 80, then there will be families whose consumption whose expenditure will be 55, 60, 65, 70, 75, and I'll take the summation of it, and when I'll take the average, I'll get 65. So the conditional mean of y for the value of x is 65. For conditional mean of y for the value of 100 is 77. This is a conditional mean. So we are getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 conditional means are there. What is the concept of unconditional mean? I'll take the summation of all this and then I divide it by 60. Then I get the value which is 121.20. And this is unconditional mean because this value is not dependent on any particular value of x. Symbolically, it is written as E, Y, x, which is read as expected value of y given the value of x. We have to read this as expected value of y given the value of x. So you can see for 80, for income of 80, this is the dispersion in the data and we are trying to pass a line. Now because of this, this line may be having some errors because the line can pass through like this or it can pass through this. So the dark circle here shows the conditional mean against mean of y against the various values of x. So this is the conditional mean. So here 80, the income was 80 and the conditional mean was 65 and we are trying to pass a line in this way. So if we join this conditional means, we get population regression line, also known as a population regression curve. Now this expected value of y for the value of x, we will denote it by some function fxi. So it is this fxi is a linear function. Equation 1 is also known as a conditional expected function or a population regression function or a population regression for short. It merely states that the expected value of the distribution of y given xi is functionally related to xi. Now this expected value of y for the given value of xi, which was fxi, now I'll represent this by a linear equation. Beta 1 and beta 2 are fixed parameters known as regression coefficients. This is known as intercept and this is known as slope. Now let's try to understand why there is an error in any model. Say for example, we can measure the blood pressure of a person by using a spigonmanometer and a regression equation, which is blood pressure is equal to 120 plus 1.1 times of age plus 0.3 times of weight. This is just a hypothetical equation which I have used to explain you what's the concept of error. This equation I have made after running the data on some samples. I'm again repeating there is no such equation. I'm just trying to explain the concept of model and the error. Now this is the actual blood pressure and this is a theoretical blood pressure based on the data which we have got. Now there will always be a difference between actual blood pressure and predicted blood pressure because these two can never match. The reasons are many, which we will see later on, why there is an error in the model. Now whatever is left out is an error. You cannot avoid error in the model. There will always be an error in the model. Now if there is an error in the model, we want to minimize this error. The entire objective of the ordinary least square is minimizing this error. You can see here, these are the observed points and I'm trying to pass a line in such a way that it can cover maximum point. So this is the actual observations and this is the predicted and whatever is the difference is the error. So y is equal to beta 0 plus beta 1 x plus error. So the stochastic specification of the population regression function is deviation is equal to observed value minus the expected value. Observed value is a phenomena and the expected value is a model. Phenomena does not have any functional form. It is a model which tries to explain phenomena by using the explanatory variable. We don't have any equation for the phenomena. For example, global warming. We don't have any standardized equation. We are just trying to explain this phenomena with the help of some model. Now, mu I is equal to the observed minus the expected, where the deviation mu I is an unobservable random variable taking positive or negative values. It is also known as a stochastic distribution or the stochastic error term. The term random, that is a random error, is a synonym for the term stochastic. A random or stochastic variable is a variable that can take on any set of values, positive or negative, with a given probability. Many books use this interchangeably. Stochastic, random, white noise, and non-systematic errors, they are all synonyms of each other. Now the question arises that why there is an error. The first answer is vagueness in the theory. It may be possible that we are not in the position to consider all the independent variables which are affecting the dependent variable, and therefore the error exists in the model. Second, unavailability of the data. Third, core variable versus the peripheral variable. It is possible that individually independent variables may be affecting the dependent variable, but jointly they are not affecting. For example, individual salary has its effect on consumption, but when I talk about family salary, it does not affect the consumption as much as individual. Intrinsic randomness in the human behavior. There are some variables which are bound to be left out because of human behavior, or rather, we are not in the position to quantify such variables, and therefore, intrinsic randomness is always there. For example, uh, lifestyle, I cannot define it appropriately. Poor proxy variables. I want to capture loyalty of an employee, and therefore, I have used the surrogate variables to represent this. The surrogate variables are absenteeism and productivity. It may happen that these variables, which I have used to represent loyalty, do not represent loyalty 100%, and therefore, these proxy variables may generate an error. Principles of passivity. We want to create a model by using 2 or 3 independent variables which are having a good explanatory power in comparison to taking 6 to 7 variables. The thing which we should remember in creating a model is we should create a parsimonious model rather than over parameterized model. We have specified the wrong functional form. Means that the phenomena is following the quadratic structure, and we are trying to model this relationship by using a linear, and therefore there will be an error in the model. Now there are some assumptions of the classical linear regression which we'll have to follow. The model is linear in the parameter. It's a very simple thing which we should understand. Y is equal to beta 1 plus beta 2 x square. This is non-linearity in the variables. This is non-linearity in the variable. In my previous videos, I have already discussed about this. This you can definitely handle, and this is linear. How I can handle this? Y is equal to x square. If I take log on both the sides, log y is equal to 2 log x, and therefore now it is linear. The regression model is linear in parameters. It means that it should not have the power on beta 1 square or beta 2 square. If it is having a power on this, then it is a non-linear, and therefore we will not be in the position to model such relation. Second assumption, x values are fixed in repeated sampling. If we carry out this study again, the same x values should be repeated. This is the reason why our regression analysis is called conditional regression analysis, because we are repeating the same value again. Very simple thing. What this assumption is, that suppose we carry out the study again, make sure that the observations are taken at the point 80, 140 and 220. Zero mean value of disturbance. That is for the given value of the x. the mean of mu, that is the error term, should be equal to the 0. Or in other words, it should be normally distributed. For example, if I say that if I plot the graph of mean, then it should be normally distributed. It means that the possibility of committing very large positive errors should be very less, and the possibility of the committing very large negative errors in the model should be very less. This is mean and this is standard deviation. The homoscedasticity or equal variance means that the variance the variance of the error term should remain constant, that is sigma square. So the given the value of x, the variance of mu I is same for all observations. It should hold constant. There should not be autocorrelation between the two disturbances. That is, for given value of xi and xj, the values of mu I and mu j should not be correlated with each other, where COV is covariance. You can see we are passing a line in such a way that it is passing through the mean of this. Assumption 6, zero covariance between mu I and xi. The number of observations, that is assumption number 7, the number of observations n must be greater than the number of parameters. Assumption 8, variability in x values. X should change, and yes, we have changed the values of x. So one observation was taken at 80, then 90, then 125, such way. Assumption 9, the regression model is correctly specified. It means that the model, say for example, phenomena is following a linear structure, and we are trying to, the model, rather the phenomena is having a quadratic phenomena. It's a quadratic phenomena, and we are trying to measure it by using a linear relationship. This is not correct, and therefore the regression model is correctly specified. There is no perfect multicollinearity between the two independent variables. This thing I have tried to explain it by some memes. Let's try to understand. The error should not increase or decrease. The error is increasing or decreasing, it is known as heteroscedasticity. There should not be any correlation between present error and the previous error. It is there, then it is an autocorrelation. Two independent variables should not be correlated with each other. If they are, then it is a multicollinearity. The errors should not be increasing. See, errors increasing, mu square. This is the linear trend. This is a parabola, and this is a quadratic. If the error is showing some trend, it means that, say for example, I have tried to capture this relationship between y is equal to alpha plus beta 1 x1 plus mu. If the error is showing a pattern, this pattern, it means that there is some variable which has been left out in our equation, and because of this error is showing a pattern. Any omitted variable which is there in the equation, any omitted variable which we have not considered, its variance will be captured by mu, and therefore mu will show the pattern. What is the ideal residual curve? This is the ideal residual curve in which the error is randomly distributed. Say for example, if I pass a constant line, then the errors may be positive, negative, positive, negative, positive, negative. Now I want to estimate the sample regression function based on the population. And therefore, it may be possible that I may be drawing 2 or 3 samples from the population, and I'm trying to make the sample regression from these different samples. And because of this, I may get different regression functions. So the question arises, which SRF, sample regression function, you will select. So I'll select the sample regression function which is based. Based means blue. That is based, linear, unbiased estimator. So out of several regression functions, 1, 2, 3, I am picking up y hat. So the best one is known as y hat. So I am trying to estimate the population regression function with the help of sample regression function. So this is a population regression function. Expected value of y for the given value of x is b1 plus beta x to xi. Now this you cannot estimate because the population is large, and therefore you are trying to estimate with the help of SRF, which is y hat. Please remember, y hat is a sample regression function in which now I'm using beta 1 hat plus beta 2 hat xi. What's the concept of ordinary least square? Let's try to understand. Phenomena is equal to model plus error. It is next to impossible that we can fully explain any phenomena, and therefore any phenomena will have an error. So yi is equal to yi hat plus ui hat. So hat is equal to yi plus the observed value minus the expected value or the estimated value. Now the concept of ordinary least square is we want to fit a regression line in such a way that these errors which are there, this is an error. We will take the square of these errors and we will take the summation of it of this. The line which is having a least summation of errors. For example, we are having these two lines, 1 and 2. We will try to pick up the line whose summation of errors is minimum. We don't have to do this. The software will take care of this. It will pass a line in such a way that the error is minimized. So this is the error term, the stochastic error term, that is a random error. Now, if I talk about y mean, this is y estimate, then and this is the observed value. So if I take the difference of observed value to the y mean, it is SST. SST is total sum of squares. Please remember these terms. It is a total sum of squares. Now, if I take the difference of observed and expected, that is observed and estimated, it is SSE, sum of square of errors. Sum of square of errors. If I talk about SSR, that is y estimate and y average, it is SSR, sum of square of regression. Okay. This we will see later on. Now SST, total sum of square, is equal to SSE plus SSR, that is sum of square of regression. Now as far as possible, we should try to minimize this part. This is unexplained variance. This is explained variance. Or rather, our model is able to explain the phenomena how much. So SST is equal to total sum of squares, that is the measures of variations of the yi values around their mean y. SSE is error sum of squares, variation attributable to the factors other than the relationship between x and y. SSR is regression sum of squares, explained variance attributable to the relationship between x and y. This is the technical definitions which they have given. Now comes the R square. R square is sum of square of regressions divided by sum of square of total. It means that explained variance divided by total. Explained variance with the help of independent variables. That is how much independent variables x1 and x2 are able to explain variance on y. This R square is known as a coefficient of determination. Also known as, or rather, it is a dependent variable. It is a total variance in the dependent variable that is explained by variance in the independent variable. The coefficient of determinism is also called as R square and is denoted as R square. This we have seen. The range is 0 to 1. When we are having only two series, your coefficient of determination is equal to simple correlation coefficient. Let us try to understand this thing by a Ballantyne's view. The y independent variable is there. Sorry, y dependent variable is there and x independent variable is there. When I say y, so x is able to explain y this much. Here, the explanatory power has increased. Here, there's again increase. And therefore, we want such x whose explanatory power is more on y. We don't want such terms because this is the perfect multicollinearity and this will end up in trouble. Now, there are some problems associated with R square. The spurious regression problem. R square cannot identify that is X actually able to explain Y or not. Now we have taken in our equation two variables which are not actually related with each other. They are unrelated, but they exhibit strong behavior. This R square will be misguiding us and it will give a higher value. The high correlation of xt with another variable zt. It might be possible that there is zt which determines the behavior of yt and is highly correlated with xt, but we have not included in this equation, but still r square is high. Correlation does not necessarily imply causality. No matter how high the value of r square, this does not suggest that there is a causality. Time series equation versus cross section equation. Time series equation almost generates higher R square values than cross section equation. This arises because cross sectional data contain a great deal of random variation, which makes ESS small relative to TSS. Random variation is very high. ESS is sum of square of errors. On the other hand, even badly specified time series can give R square of 0.99 for spurious regressions, as there may be many terms which we may have included. For example, in our equation, I have included the lag of lag 1, lag 2 and lag 3, and as we have included more variables, the R square will increase. Low R square does not mean that it is a wrong choice of xt. The functional form that is used may be inappropriate, or in the case of time series, the choice of time period might be incorrect and lag terms might need to be included. So low R square does not suggest that there is a wrong choice of xt. We have generated R square from two different equations. One is yt is equal to alpha 0 plus beta 0 xt plus error. And the second is natural log yt is equal to alpha plus beta ln xt plus ut. Now, we cannot compare R square of these two equations because the functional form of these two equations have changed. So this was all about classical linear regression model. For more videos on econometrics, kindly subscribe to my channel. You can follow me on LinkedIn and Twitter.